Hello, I am Aditya Kumar. I work as a software engineer at Facebook. In this video, I'll be talking about code size compiler optimizations and techniques for embedded systems. On resource constrained devices, for example, mobile phone and other small devices, the space for code for an executable is pretty limited. And code size optimizations have been getting more and more attention in recent years. So there are many compiler optimizations which reduce the code size, but they are not always available at a specific optimization level. Some of them are available at a specific optimization, but some of them are not enabled in many cases. So we need to learn about them to get advantage from the compiler. Apart from that, there are many software engineering techniques which can be used to reduce code size as well. I'll be talking about them. When we are talking about code size, we can classify all these techniques into 4 parts. The first one is the classical compiler optimizations. In the second, we can classify them as optimizations on standard libraries. I'll be talking about C++ standard library, but many techniques can be used in other libraries which are probably used in many components in your work, in your system. The third one is the source code optimization. And the last one is getting more insight into source code to squeeze even more code size out of the executable. So let's talk about the compiler optimizations first. These are the easier ones. Most of them you're most likely familiar with already. In the popular compilers like GCC and LLVM, they provide compiler flags -OS. OS is for optimizing for code size. What most common optimizations flags are -O1, O2, and O3. Those are for performance, but OS is for code size. In LLVM, we have additional optimization flag, which is -OZ. -OZ optimizes for code size, even in the cases where it may compromise performance. But in some cases, we need that. So LLVM provides that flag as well. The third one is -F no function sections. When compiler generates binary, it is possible to have every function in a section. So there is a section is a part of executable which can be treated separately by a linker. So I don't want to go into like more detail, but we can ideally keep every function in a section. That helps with debugging and runtime instrumentation, things like that. But we don't always need them. So if you pass F no function section, then the compiler will put all the functions in together in a text section, and that will save a lot of code size. The next one is F no unroll loops. Loop unrolling is a widely used compiler optimization which improves performance on many instances, but it increases the code size. In cases where we don't care about performance of loop, we can disable them. The fifth one is F no exceptions. In C++ code or C++ heavy code, exception handling code is generated all over the place in every translation unit, because there is some information that is required to be present in the binary such that when an exception is thrown, the runtime would be able to walk up the call stack and provide relevant information or handle that exception. But in many cases, we don't use exceptions, so we can just disable them. That will save code size. Just to be careful that we cannot use a throw or try block if the exceptions are disabled. So you have to be like really not use exception in the first place. That way the compiler will not generate extra like useless code, which we are not planning to use anyways. The next one is fno RTTI. So in C++, when we use dynamic cast to take the advantage of runtime polymorphism, the compiler generates some metadata in the binary, and that is used to infer the type. But in many cases, we don't use dynamic cast all the time. So we can just disable RTTI. RTTI stands for runtime type information. So if we are not using dynamic cast, we can just get rid of that and save a lot of code size. The next one is to limit the inlining optimization. What compiler does is it can inline a piece of function code into another function. So when we make a function call, and instead of making the call, it'll just kind of copy paste the code into the caller. What it does is it improves the performance quite a bit. Inlining is one of the most common optimizations that gives like huge performance improvements. But when we are looking for saving code size, we don't need to inline them. So we can disable them. But disabling them can have huge performance regressions. What we can do is we can reduce the inlining threshold. So when we reduce the inlining threshold, not a lot of functions will get inlined. So the bigger ones will not get inlined, the smaller ones will still do. That way we can still save a lot of code size. And the last one is fno jump tables. When we write switch statement in C++ programs, the switch statement gets generated as a jump table in the final binary. In several cases, jump table has more code size overhead. In principle, we can also generate a switch statement as a sequence of if and else statements. So in many cases, the if and else statements consume less code size. So you can try this. This is not guaranteed to reduce the code size, but in some workload it does. So I would encourage you to try and see how it goes. There are some compiler optimizations which are only available in GCC. So it is not in LLVM, these flags. But it is good to know if you are using GCC. GCC is a widely popular compiler, and it is quite commonly used in the RISC-V space as well. So it is good to learn about these. The first one is m call prologs. What this compiler optimization does is it does not generate the frame setup code. What do we mean by frame setup code? When the compiler generates the code for a function, it generates a sequence of code in the beginning of the function, as well as some sequence in the end of the function. Those instructions are mostly for saving some registers, which are called the callee saved registers, and then again at the end they restore those, basically load them again, so that the caller, the parent function, can use those registers as if they were never changed. So what this flag does is, instead of generating those sequence of instructions in each function, it just generates a function call, and all the functions in the program will call that same function. So it saves huge code size, but of course it has a little bit of performance overhead. But in embedded systems, embedded space, this flag is widely used. The second one is -m int8. This flag is very risky to use, but it's good to know. You can guess from the flag. What it does is, instead of generating 32-bit for an integer, the compiler assumes that the integer is only 8-bit. And of course, this is not language compliant. But if you're using integer which you know that does not have a get any values longer than like 8 bits, then we can use them. But it is quite risky, and debugging a code which introduced a bug in mint8 it is a very difficult error to debug, but it can be used as well. The third one is -m save restore. This is the same as -m call prologue, but in GCC an additional flag was added only to support RISC-V. I'm not sure why this was added. I would expect these two to be the same and just work on an architecture specific basis internally, but this is how it is. The fourth one is -f reorder blocks algorithm equals simple. We can think of a function as a sequence of, we can like think of a function, a sequence of code in a function as a control flow graph. So we can imagine that a sequence of instructions without branches are node and the branches are edges in a control flow graph. And when the compiler tries to generate binary for this control flow graph, it has to put basic block in some particular order. And compiler has a set of heuristics to reorder these basic blocks. Now, different order can incur different code size overhead. So the simple algorithm, like reorder blocks algorithm equals simples, incurs the least amount of code size overhead. So this can save code size as well. I'm not sure how much this will save, but it is good to try. And the fifth one is, this is a special feature of GCC. What it does is it provides access to some of the internal compiler optimization heuristics by means of this flag called --param. So in compiler, whenever as a compiler optimization writer, what we do is when we write an optimization, we have to choose a set of heuristics, like what is the threshold of inlining, how much loop we want to unroll, etc., etc. Now, we don't hard code those in the optimization, but we keep a flag that can be tuned by external user. These are those flags, and they are not widely used by application developers. But if we are looking for some like specific, like you want to extract extra things out of compiler, like performance of code size in this case, it is good to know about these flags as well. So the first one is inline min speed up equals X%. X can be 10, 20%, whatever. Yeah, so if we want more speed up, that means more inlining will be done. So that code size, you'll have more code size overhead, but lesser the percentage, smaller the code size. Similarly, the second one is max inline instruction single is 400. So what it does is basically when we want to inline a callee into the caller, the callee function has to have a certain threshold of code size. If the callee function is longer, then the compiler will not inline them because it will increase the code size of the caller. So, and the threshold is 400 here, and 400 is counted by some heuristics inside the compiler, but we don't want to know the exact details. What we want to know is if you increase the number, more functions will be inlined. If you decrease this number, like 300, less functions will be inlined. Similarly, the third one is when this recursive inlining. Currently the number in GCC is 450. If you increase them, you will get more inlining, and vice versa. The fourth one is max grow copy basic block instructions equals 8. So there are optimizations like jump threading and like tail duplication. In these optimizations will copy basic blocks. And if you want to reduce the number of copies, so if you reduce 8 to like 2 or 3, the code size overhead will reduce, but some of the optimizations opportunities will be missed. The second to last is inline unit growth is equals 30. This is per translation unit. So when we inline a translation unit, basically a .c or .cpp file, can only grow by so much, and that heuristic is controlled by this flag. If you increase them, more functions per translation unit will be inlined. Then the last one is IPCP unit growth. This is interprocedural constant propagation, if I remember correctly, and this is 10. We don't want to know how this number is calculated internally, but we only want to know increasing this will increase the code size and decreasing this will reduce the code size. The numbers I provided here are hard coded in the GCC compiler, so you can. This is the default value, and I would encourage you to try these and see how much code size reduction you get. There are some optimizations which are not enabled by default. Some of them can be enabled, and you can try them out. The first one is FLTO. This is basically enabling the link time optimization. What it means is, when we compile a program, the compiler works on one translation unit at a time. But what that means is, when we have a lot of source code files, like 1,000, it'll compile all of them individually, and the linker will put all these object files together. That process is called linking, and then generate the final executable. Obviously, when we do this, we miss so many opportunities which are cross translation in it. Like if we're calling one function from a file, first file to another file, the compiler does not know how this call are put in the context. So many of the optimization opportunities are missed. But when we put all these files together and compile this whole thing as one giant program, that way we can take advantage of like larger visibility into the source code. And FLTO, the link time optimization, basically does that. Link time optimization reduces code size by quite a bit by having access to more information and like more like constant propagation, devirtualization, inlining. So it will reduce the code size by quite a bit. Thin LTO is a feature in LLVM only. It is not in GCC. It is a it also does the link time optimization, but it is not as aggressive as the full link time optimization. But you'll still get almost like, I don't know, like 80 or 90% of the optimization in thin LTO, but not everything. This is done to this optimization was enabled to reduce the build time. You can assume that when we put all these object translation units together, the memory footprint, the compiler will become slow, and some of the algorithms in compiler which are quadratic, they slow down the compilation process. But thin LTO reduces those overheads and still gives us reasonable optimization. This will also reduce the code size by quite a bit. The third one is identical code folding. There are many different variations of this. In GCC, it is called FIPA ICF. And in LLVM, there is an optimization called merge function. And there is one more which is in upstream LLVM, which has not been merged. But if you have a compiler team, I would encourage you to try them out. It will reduce the code size by quite a bit as well. Essentially, what they do is you have functions which are kind of similar. And what we can do is we can put them together and like kind of deduplicating them. And like for identical functions, they'll be merged, completely deduplicated. But if there are a little bit of dissimilarities, then we can put if and else branch. Compiler knows how to do that and conditionally execute the code depending on where the functions were called from. The fourth one is GVN hoist. This is only in LLVM. This is a optimization to hoist the code from else, then and else branches into the parent if branch, but like more generic and more saves more code size. GVN sync is just the opposite of GVN hoist. It just syncs the code from common ancestors. sorry, not common ancestors, like multiple ancestor into the post dominator, but this also saves code size. The next one is machine outliner. What it does is it basically outlines sequence of code into a separate function call. And if many functions have the same sequence of code, then they get only one function will get called, and it will save a lot of code size. The last one is called hot cold splitting. This can save code size, but you have to use this in conjunction with merge function or identical code folding. What hot cold splitting does is it moves out certain piece of code from a function, and those pieces of code are actually cold, means they are less likely to be executed. By outlining them, it actually improves the performance of the original function. But when we outline the cold pieces, it is likely that similar cold pieces are available in other functions as well. And they can be deduplicated by optimization like merge function or identical code folding. The last 4 optimizations I talked about is only available in LLVM. Now, moving on to the second category called C++ library optimizations. C++ libraries tend to have a lot of templates and header only libraries as well, like Boost, libc++, eigen. When we put the definition in the header file, these definitions get generated in all the translation units, and they incur code size overhead because those functions can get inlined, and there's a lot of code bloat. And this is one of those things that receives like a huge amount of complaint from developers who care about code size. So what we can do is, we can outline those functions into a CPP file. So that will reduce these issues. The second issue with C++ like template only libraries is that the templates will get instantiated in each translation unit, and again incur code size overhead. So if we explicitly instantiate them in one of those source files like .cpp files, then the code size overhead will reduce. The third approach is to put attribute no inline in those function definitions. That way, the compiler will not inline them, and then that way it'll still get the same advantage of reduced code size. The next category is source code based optimizations. As I talked about that in the standard library optimizations as well, like we can move the function definitions from header file to CPP file. And that way it will not get inlined, and then we'll save code size. C++ heavy code will have many other functions which we don't see them because of abstraction penalty, like constructor, destructors, and the copy constructors. And with C++ 14, 17, we have like many other, like rule of 7 or something, like there are too many constructors. And depending on how the what the members are of a class are, you may end up with all those constructors. So and they will incur code size overhead. Like imagine a header file which is widely used, and it has all those definitions. So those definitions will get used across all the users and incur code size overhead. We can explicitly instantiate those definitions in the CPP file, and there are many tricks to do that. You can search online. And similarly, explicitly, we can instantiate those templates and save code size again. One more thing to think about is using cheaper data structures. In product code, you might have class definitions which have like unnecessary variables, or look out for variables which are only used in debug mode, and we are shipping this to production like regardless, and maybe they are getting missed. Here I will be talking about C++ standard library data structures like vector, dec. These are very commonly used, but these have more code size footprint than standard list. This is a doubly linked list. People tend to use vector over list all the time, but when we don't care about performance, in those cases, we don't have to use vector or dec. List is much cheaper. I'll share the numbers in the next slide. Similarly, unordered map and unordered set are getting more and more widely used. Basically, people follow a common wisdom, and then like C++ gurus, and they talk about that use vector, use unordered map all the time. But what if we don't care about performance and the code size is more important? Then we don't have to use them. These pointer-based data structures like list and map, they have much cheaper code size footprint. And here are the numbers of map and list versus unordered map and vector. So this is a very small program just to show the numbers. It's a small program. We have a map and we are assigning a variable and returning that one member just to not let compiler delete everything. The compilers are pretty smart, so they can delete. So just returning m of 0 just to keep those code. And you can see that the code size of standard map here is around 14 kilobytes. And on the right side, we see the code size overhead is 15 kilobytes. So 1 kilobyte for this small function, which can be pretty big in a large application. Like you have to keep adding these up. Similarly, for standard list, it is the small for loop, and we are just adding elements and returning one variable so that the compiler does not optimize them. The code size overhead is 13 kilobyte, and on the right side, standard vector is around 14.3 kilobyte. It is possible that in your case, vector is having low code size compared to list. I'm not guaranteeing that it will happen, but this is, I'm providing an insight to just not blindly use any data structures. Look for what is more important. Is it code size more important? Then you have to evaluate that maybe whatever people are saying everywhere is not the right thing to do. So yeah, basically measure and then make the right decision. Okay. The next techniques are to get insight into the code, source code. In a large application, we'll have multiple developers working on them. People start working on a project, they leave in between, they move to another project, and you're shipping dead code all the time. Sometimes you have features which were widely used, and then you got new features. The old ones are still in the code. It is not user visible, but basically shipping more and more dead code. As any large project evolves, we'll have more and more dead code. And for compiler, it is not possible to find all those dead code, simply because the way visibility of C++ function or C function works, functions by default are externally visible. The compiler has no way to know if a function is dead. In some special cases, the compiler knows, like if the functions are internal, static functions, it can be inferred. In link time optimization, many functions can be found to be dead if they are, but there'll be plenty of dead functions. So what can we do? One approach would be to get data from production, like instrument each function, like basically the larger ones, not the smaller ones, and get data from production and see if that function is getting widely used or not. And over a long period of time, over multiple devices, we'll learn that which functions are used and which functions are very less used or not used at all. If a function is not used for some period of time, it doesn't mean that it is dead. For example, if you have error handling code, most likely if you have a great application, it was never called, but you still want to keep them because you never know. but it'll reduce the area of focus like dramatically. Instead of focusing on 1,000,000 functions, you're probably focusing on 10,000 functions. And that way we can put engineering effort to manually delete them. And often I find that deleting one function leads to the effect is cumulative. So you might end up deleting more and more, and you'll save a lot of code size. I recently wrote a very small compiler instrumentation, which does basically this. It instruments the entry of the function. It is very cheap. It is the cheapest possible instrumentation you can get. Basically, the overhead is like 3 or 4 bytes per instrumentation. Sorry, it is around 5 bytes per instrumentation. And so this is just the core of the patch, and then there'll be some infrastructure around it, like you have to collect the profile and like basically keep the debug information and like correlate that, okay, this line of code corresponds to this instrumentation data you got from the production, and then find out what functions are basically have been executing less and which are more popular. But this can help you detect code size by getting real data. Another approach is to move less frequently executed code into shared libraries. So this also helps reduce the launch time of the program. Like in embedded system, launch time is also pretty important, because yeah, like your small memory and working set, like you don't want the working set to be large, but most of the time you have like kind of 80-20 rule. 80% of the code is not used. So if somehow you know by getting profile or some other measure that functions are cold, then we can move them into separate shared library. That way, basically the initial launch time and the code size will reduce as well. This is another approach called binary compression. Basically, pieces of code which are not widely used, we can compress them, and in case they are about to be used, basically we uncompress them and then load them by like dynamic library loader APIs. I have not personally used this. This is not my library also, but I have found this through my research. So if the code size issue is getting so troublesome, then you can use this. You can use any other popular compression library, but this has a low overhead, like very low memory footprint, and decoding is faster. It may not give you the best compression, but in case code size is a lot of trouble, I would encourage you to try this as well. Finally, I have some references of the things that I was talking about, like compiler optimization that I wrote. Maybe they are in the review, so I put them there. One of the most common resources is the GCC manual page. It has a ton of optimization flags. If you're struggling with code size, I would encourage you to read them. They have a very nice documentation. So man GCC or in your machine or online as well, they are pretty helpful. That's it. Thank you.